Our bell work for today asks how the distance between the objects affects the gravitational pull on each other. So we've completed the gravity gizmo and we have worked on the gravity notes. And at this point, we should know that as the objects get closer together, they have more gravitational pull, and as you get them farther apart, they have less gravitational pull. Now, our fact for today is that temperatures in a lightning bolt can hit about 50,000 degrees Fahrenheit, and they carry up to 1 billion volts of electricity. Now, that quick heating of the atmosphere actually causes the rumble of thunder that you hear. When you see lightning, you hear the thunder. It is because that temperature heats the atmosphere very quickly, causes the air to expand very fast, creating the boom that you hear we call thunder. Now, we've been working on this state standard for quite some time. Forces between objects act when the objects are in direct contact. That would be the friction we talked about, and when we're pushing and pulling on objects. And also when they're not touching, this would be the field forces we've been discussing. That would be the electrostatic force we started talking about yesterday in class, and the gravitational forces that we've been talking about. By the end of class today, you need to be able to explain the relationship between electric charge, the amount of charge, the distance between the charges, and how much force there are between the two charges. So here we have a couple examples. We have the girl with the balloon rubbing on her head. We did this in class yesterday when we tried to use the force and make the pop can move by rubbing a balloon on her head first. You probably have been shocked grabbing onto a metal doorknob after walking across a floor, maybe in socks. And hopefully soon we will be able to play around with a Van de Graaff generator to see how we can build up a static charge. Now, we've been talking about field forces. We use field models to explain how objects that are not touching can exert a force on each other. Again, this is the gravitational pull we've been discussing. It's also the electrostatic charge that we've been discussing yesterday and we're going to talk about today. And it'll also be applied to magnets, which we'll get into tomorrow. So every object is thought to have a field surrounding it. And when you put another object in that field, there's a force that is exerted on the object, and it can change the object's motion. So forces, balanced and unbalanced forces, can change the object's motion, but these forces don't actually have to physically touch the object for it to affect the motion. Remember, objects that are already moving or objects that are at rest are going to keep doing what they're already doing if the forces are balanced. So if it's already moving, it's going to stay moving. If it's not moving, it will not move if the forces are balanced. You need an unbalanced force to change the motion. If it's not moving, it could make it start moving. And if it's already moving, it could slow it down, speed it up, cause it to change direction. Now, in order to talk about charges and to understand how charges interact, we need to understand the setup of what's called an atom. Now, everything around you, if you look around, everything around you is made up of atoms, whether it's alive or not. So you are made of atoms. The pencil you're writing with, the chair you're sitting in, the floor, the walls, everything is made of atoms. The definition of an atom is the smallest part of an element that can be identified as that element. So basically, if you chop stuff up enough, the atom is the smallest thing you can have and still be the element. Now, if you notice, we have the structure of the atom here on the left. We've got lots of blues and reds in the center, or the nucleus of the atom. You see where it says neutron and proton. And then we have these little yellow things flying around the outside. We call those electrons. Now, make sure that you never trust an atom because they make up everything. Now, the parts of an atom, if you remember the word pen, that will help you remember the parts of an atom. We have protons, the P, electrons for the E, and neutrons for the N. Protons are the positive charges, electrons are the negative charges, and neutrons are the neutral or no charges. Now, we just saw in the last slide that protons and neutrons are in the nucleus. They don't move. The electrons are the ones that are flying around in an electron cloud outside of the nucleus. These are the ones that can be transferred from object to object. When we rubbed that balloon on our head yesterday in class, we were taking electrons from the hair and putting them onto the balloon to make them a negatively charged balloon. So down here in the picture, we have a bunch of electrons. They're just bumping into each other as they're flying around. We have a positive charge comes along, and one of the electrons says that the others are too negative, and that negative charge is out of here. Obviously, it's being attracted to that positive charge. Now, electric charge is the electrical property of matter. It creates the electric forces that we saw yesterday in class, that's static electricity, and also the magnetic forces that we're going to be talking about soon. These electric charges can be either positive or negative. You probably know from working with magnets that if you have two of the same pole, they don't want to be together. They try and move apart. They repel each other. The same is true of like charges. If you have two positives, they try to get away from each other. Two negatives, they try to get away from each other. They don't want to be friends. They try and move away. Unlike charges, or a positive and a negative together will actually pull together. And we'll see in a minute why that happens based on their electric field. We measure electric charge in coulombs. You should have seen that yesterday in the electrostatic charge simulation. So negatively charged objects are going to have more electrons than protons. Remember, electrons are the negatives. In a neutral object, we have the same number of electrons and protons. So they kind of even each other out. Negatively charged objects are going to have more electrons, more of those negative charges. Positively charged objects will have less electrons and more protons. So you have more positive charges than negative charges in the object. So up here on this comic, it says, "You've lost an electron. Are you sure you're all right?" And the other one says, "I'm positive." Now, you're probably familiar with conductors and insulators. When you're looking at creating an electric flow of electricity, you're going to need something for the electrons to flow through, and conductors work very nicely. These are just materials that allow those electrons to move freely. It's like you're roller skating through, very smooth, move through it very easily. Insulators, on the other hand, would be materials that are going to stop or are going to block that flow of electrons. It's not going to be very easy for them to get it through there. So conductors, many metals are great conductors. For insulators, wood would be a great insulator. Now, we charge objects a couple different ways. Yesterday, we did friction, where we were rubbing the objects together. We can also do conduction, where we are going to have a charged object, and we just touch it to another object, and the charge will transfer. We also have induction, where the charge is transferred, but it kind of jumps from one to the other. It doesn't come into direct contact with the object. The conservation of charge is basically in a closed system, one that you can't add anything to or take anything out of. You will have a conservation, or the overall charge will stay the same. It's just going to move between objects. It won't add any more to the system or take any away. So there's a conservation of charge. Overall charge in that closed or isolated system remains the same. Now, think back again to our I can statement for the day. We want to make sure we know how the electric force, how the amount of charge, and the distance between the objects all relate. So we're going to get into that right now. Electric force is the attraction or repulsion. Are they coming together, or are they pushing apart? It is determined by how much charge is on the object and the distance between the objects. This is Coulomb's first law. It's basically a formula that tells us those electrical forces between the objects. And again, we worked with that yesterday in the electrostatic charge simulation. So if you have the objects closer together, the electrostatic force will be stronger between the objects. So closer together, stronger force; farther apart, weaker force. This should sound very much like the gravitational fields we talked about. Put the objects closer together, you have more gravitational force. Spread them apart, you have less gravitational force. So same thing is true with the charges. If they are the same charge, you put them closer together, you have more force. You move them apart, you're going to have less force. If you have more charge on the object, you will have more charge is a stronger force, less charge is going to be a weaker force. You should have seen this in the simulation yesterday. As you increase the charge, the force between the objects increased as well. Stronger charge equals stronger force. Again, this is our I can statement for today. Now, we mentioned the electric fields earlier. Basically, this is just the region around the charged object where if you were to put another object in there, there would be a force exerted on it. We represent this with a circle for the object and then the force lines coming out of the object in this case. And if you look at how many force lines are coming out, that tells you how much charge is on the object. So as you see here, charge letter C has a lot more lines of force coming out of it, so the charge is much larger on C than it is B, and then B is even bigger than A. Now I want you to notice the field lines in these two pictures here on the right. The positive charges have the field lines going out from the charged objects. Now this is going to be important for why these things interact the way they do, with the positive and negative repelling each other, and why positive and negative together actually attract. So positive goes away from the charge, and negative actually comes towards the charge. Now this picture down here on the left side is showing you that this is a three-dimensional field. We've been looking at these pictures so far, and they've been the flat two-dimensional drawings. These fields are actually in every direction out from the charged object. So here are some force field diagrams. We have the positive charge where the field force is going out from that charged object, and then we have the negative charge up here where the force fields are going into that negative object, negatively charged object. So you can see how these things are interacting with each other. When they are opposites, they're actually attracted to each other. Now on the right side here, we have two positive charges. With both of them coming in the outward direction, they bump into each other, and that keeps them from going together like we have here on the other side with the opposites. The force fields are actually bumping into each other, and those charges are being repelled by each other. Now, static electricity is something you probably are all familiar with. You have this anytime you are walking across the carpet and you grab a doorknob and you get a slight shock. Or you do it on purpose and rub your feet on the floor and then walk over to your sibling and touch them and they get a little jolt. This happens to everybody. It also can make your hair stand up when your hair gets positively charged because you've pulled off the electrons with, say, the balloon we rubbed on our head yesterday, or even a comb can do this. Now, it's called static electricity because static means it's not moving. Those electrons are building up, but they're not moving. Now, they will move when you have a static discharge. We'll talk about that in just a second. Now, you probably all know by now I love The Lion King, so of course I had to put this little comic in there. And in the true fashion of cats, both big and small here, we have another little cute kitty that has been tortured. We've got some static electricity going on. So it says, yeah, real funny, rub me on the carpet and then put me in the shipping box. You will pay for this. So rubbing the cat on the carpet has created a situation where you have a negatively charged cat and you put him in with the packing peanuts, which are going to be sticking to him because there will be some positive charges on the part of those packing peanuts that are attracted to the cat. Now, static discharge, you guys are all familiar with this as well. That's that little spark you see when you get shocked when you touch the doorknob. In a larger scale, you would see this with lightning. This is where we have the negatively charged cloud, the positively charged ground, and the lightning will jump from the negatively charged cloud down to the positively charged ground to even out the charges.